Good evening. Good evening.
Good evening.
Matt, can you hear me?
Barely.
Good evening.
There you go.
There you go.
How are you all? I wanted to start with the level setting here. How many of you have actually used Azure Cosmos DB? One? Anyone else? So you guys are not going to ask any questions. You are barred from asking questions. I'm just joking, you can ask. So, speaking of Cosmos DB, anyone has worked on any NoSQL database? Do you understand what NoSQL database is? Which one? Mongo?
We're just doing some code downstream to SQL.
All right. The rest, everyone has worked on SQL? SQL Server, Oracle? Which one? SQL Server? Sounds good. That gives me an idea of the audience. So, let's get started. All right, I wanted to introduce myself in case you don't know me. My name is Vaibhav Gujral. I work for Kivit as a cloud architect. I have over 13 years of experience working on enterprise class applications. I'm a Microsoft certified Azure architect. I own some other certifications as well. You can see the badges down there. I also, as Matt was saying, I also run Omaha Azure User Group here. We had a meeting yesterday, so I can see some of the faces who were there yesterday as well. Jumping onto the agenda, today we are going to cover around what Azure Cosmos DB is, and we are going to cover different other concepts around it. Probably I should walk there.
Might help, yeah.
That will be helpful so that everyone can hear.
Yeah.
Is that fine? So that's the agenda. We are going to cover what Azure Cosmos DB is. We'll see how it's structured, how partitioning works in that, how it's built, what is a request unit or RUs. And we are going to see how consistency models are, which consistency models are supported in Cosmos DB. We'll see how we can resolve conflicts in Azure Cosmos DB. And we'll see change speed, and I'll share some real-time use cases which you can utilize. How many of you work on .NET? Everyone works on .NET? .NET Core? .NET? Do you guys develop distributed applications, web applications? What type of applications do you develop? Distributed web applications. Is it do you have audience spread it across the globe or across the nation, or it's dedicated LOB application? So Azure Cosmos DB is a fully managed, globally distributed database. It's a NoSQL database, and it was the first NoSQL database which was offered in Microsoft Azure. If you don't know Cosmos DB before, there was an offering which was released earlier known as Document DB, which was later rebranded as Cosmos DB. It has guaranteed low latency, as well as it supports 5 well-defined consistency models, which we are going to talk about later. What you can see here is it supports 4 different categories of data models, ranging from key value to column family, document, and graph. On top of it, you can see it supports different API models. So what it translates into is you can use, when you're creating an Azure Cosmos DB account in Azure portal, you can opt for any of those APIs, and under the hood, it will automatically choose the data model that is supported by that API. For example, if you choose SQL, it will automatically go and choose the JSON format. If you want to use graphical data, graph data, then you go ahead and create it with a Gremlin API, and so on. And it supports some features out of the box, like it's globally distributed. It can run from one region to all the regions in Azure. As of today, there are 58 different Azure regions, and Azure Cosmos DB is supported in each one of those, and you can replicate your database in all 58 of those. It is elastic. It's super elastic. As I said, it can be replicated across the globe, and it can be replicated based on the load. It's auto-scalable. It guarantees 5 nines SLA. Do you understand what is 5.9 SLA? How much it translates it into? How much is the downtime in a year for 5 nines. For people who don't know what 5 nines is 99.999% is the SLA that it supports. So it translates into 5 minutes of downtime in an year. So, and as I said, it supports 5 well-defined consistency models, and it comes with comprehensive SLAs for throughput, for your latency. As I said, it supports multiple data models. So whenever we are creating a new Azure Cosmos DB account, we can choose any of the API that fits our requirements, ranging from all the ones listed here. You can use key value, tabular, graph, whichever is your need. One thing you can notice here is that you don't necessarily have to have an indexing policy for Cosmos DB, because it comes with auto indexing by default, but that doesn't stop you from having your own custom indexing policy, but you don't necessarily need to have one. So the question is, which API should I choose from? Which one should I use really? Because it supports 4 or 5, and it was called DocumentDB. It started with SQL, but now it supports MongoDB, Cassandra. It also exposes Gremlin. Which one should I choose? So the recommendation is, for default, if you are starting with new one, if possible, you should go ahead and use SQL, because it's Microsoft. You will get best developer experience out of it. If you are going to use graph data, go ahead with Gremlin. And if you already have other NoSQL databases in use which you want to migrate to Cosmos, you can migrate your data to Cosmos DB, and you can retain your data access layer as is by consuming the appropriate API. For example, if I already have an application which has a data access layer built on MongoDB, I can migrate my data from MongoDB to Cosmos, but I can retain my data access layer as is. I just need to go ahead and change the connection string, because Cosmos DB supports MongoDB API. Make sense? It supports comprehensive SLAs, starting from, as I said, latency. Any JSON, any entity which is of size 1 KB, 1 kilobyte, can be read in less than 10 milliseconds, irrespective of whichever Azure region you are accessing it from. And Azure Cosmos DB is the only database which gives that SLA for latency. High availability, since it's multi-region, Microsoft provides 99.999% 5 nines SLA on that. Throughput is guaranteed. We are going to talk about it later in the later slides, but one of the key features of Azure Cosmos DB is when you are configuring or creating your Azure Cosmos DB account, you are configuring the throughput upfront. What throughput do you expect from your database? And Microsoft ensures that your database gets that throughput, gives you that throughput. And same lies with consistency. As I said, it supports 5 well-defined consistency models, and you can choose either one of them. And whichever you choose, Microsoft guarantees that your database supports that. So when should I really use Cosmos DB? What are the use cases for Cosmos DB? When you have a flexible schema is one of the use cases. When you don't have schema defined, for example, if you are working on a project, let's say IoT devices where it's sending telemetry continuously, and that schema is not fixed. Those devices might change their schema. So it's a very useful use case for Cosmos DB. Do you guys understand what read-heavy and versus write-heavy workloads are? There are scenarios where you read very heavily, where your read transactions are more than write, and write-heavy scenarios are where you write heavily than compared to read. So when in the write-heavy scenarios where you need scalability, Cosmos DB is a good option to use. As I said, it guarantees low latency. So if you have use cases where you need low latency with your database operations, Cosmos DB is a good candidate there. And of course, high availability because it's globally distributed, and you can have regions. You can choose from 58 regions that Microsoft Azure is hosted in, and you can choose any Azure region which is near to your user as well. Let's understand how Azure Cosmos DB is organized whenever we are creating an account. what you're seeing on screen right now is it depicts how an Azure Cosmos DB looks like in infrastructure. It starts with an account. We call it as an Azure Cosmos DB account. The first step is to create an Azure Cosmos DB account, which is a collection of Cosmos databases. Under the account, there are databases. Within databases, there is something known as collections. And within collections, there is something known as item. So what is account? Account is the root level entity where we define the endpoint and the key that we use to connect to our Azure Cosmos DB. These are the two primary things that you need in your connection strings to make a connection from your distributed apps to the database. To create an Azure Cosmos DB account, you can log into Azure portal, go look for Azure Cosmos DB under Create New Services, and you can go to the Create New Azure Cosmos DB blade. You can provide all those details ranging from the subscription, the resource group where you want to place it in, the account name, the Cosmos DB account name that you want to give it to, the API that you want to choose here. The important point to note here is once you define a Cosmos DB account with a specific API, you cannot come back later and change it. The reason being, if you choose an API at this stage, it defines the data model for your Cosmos DB there. So if you choose Core SQL API, it automatically allows you to, it binds it with this JSON format. If you choose Gremlin, it automatically binds it with the graph model. So you cannot change it after you have created it. The only option is to create a new Cosmos DB account with a different API. And then if you can see it, are you guys able to see there are 3 different options below, ranging from geo redundancy, multi-region writes, and availability zones? I don't know, but there are 3 other options which we can configure at a Cosmos DB account level, starting from geo redundancy. How many of you have worked on Azure? Do you guys know what is a region in Azure? Region is nothing but a geographical area where they have data centers placed in. And within those regions, they have binded 2 regions with each other as regional pairs. For example, they have East US and West US, and those 2 are called regional pairs. And when we deploy our resources in regional pairs, Microsoft guarantees that both the regions don't go down together. If there are updates or there are failures or disasters, Microsoft ensures that one of the regions is still up and running. So if you enable the first option, geo redundancy, it automatically deploys or replicates your Cosmos DB account in your regional pair. For example, if I deploy my Cosmos DB account in East US region, it automatically, if I enable that option, it automatically creates a replica in West US. Multi-region writes, I have a slide later, but when I say Azure Cosmos DB is a multi-region database, that doesn't require you to go ahead and geo-replicate it everywhere. You can still have a single region Azure Cosmos DB. You can still run it in a single region. But if you want to run it in multiple regions, there are 2 different options to do it. You can either only have writable copy in one region, and you can have readable copies in all the other regions you want to, or you can have read and write replicas in all your regions. So if you want to enable read and write replicas across all the regions you want your database account to be in, you have to enable multi-write region. But you have to understand here, if you are going to enable read and write in all the different regions you have, it is going to introduce latency in your read and writes. Coming to database, as I said, database is a collection of collections. Once you define your account with the API, then you can create your collections within the database account. When we come to containers depicts either collection, graph, table, or key value, depicting based on what API you have chosen. So if you have chosen, let's say, Gremlin, your collection is nothing but a graph. If you have chosen, let's say, SQL, it's going to be your document. Once you have created a Azure Cosmos DB account, you can go inside the Cosmos. Within a Cosmos DB account, you can go ahead and create a collection in the Azure portal. You can provide the throughput here, what throughput you want out of your collection, be it document or graph or whichever you have opted for. You provide your container ID, and you provide something here known as partition key. We are going to touch upon what partition key is and why it is important. in later slides. Depending upon the container type, if it is a collection, or if it is a graph, or if it is a table, it translates into appropriate items within it. For example, if it's a collection container, it has something known as document is the item. If it's, anyone has worked on graph databases? So graph databases is like a tree-like structure where it has edges and vertices. So when we choose graph API, it automatically creates a container of graph type for us, and within graph container we can create nodes or vertices and edges. So what nodes or vertices are the different entities, and edges are the relationships which connect those two different entities. And if it's a table, it's the row and columns, and it creates rows items as an item. Apart from those standardized entities which get created based on the API and the data model, you can also define stored procedures, triggers, and user-defined functions. It's not SQL based, but you have to write it in JavaScript, because Azure Cosmos DB engine comes with a JavaScript framework within it, and we have to write all these items in JavaScript to execute. And since it's multi-region, why I was stressing upon the multi-write scenario, where we can read and write in multiple regions. If we are writing to multiple regions, there might be conflicts. So there is a process for how we can provide resolution for the conflicts having across the different replicas. I'm going to touch upon that as well in the later slide. So pretty much what we already spoke about, that it's globally distributed. It supports automatic and manual failover. Do you understand what failover is? If in case of any disaster, if something happens and your primary replica goes down, it can automatically fail over to the secondary replica so that your application doesn't gets any downtime. So the process of switching it from primary replica to secondary replica is known as failover. It provides us two options where it automatically fails over from primary to secondary the moment primary goes down, or it also provides an option where we can manually fail over from primary to the secondary. I just spoke about multi-master, where we can make all our regions writable. It supports less than 10 milliseconds of write latency. Don't get confused when people say multi-write or multi-master. It means the same thing. When it says multi-master, it means your multiple replicas can be masters. Once you have a Cosmos DB account created, you have a database running there. It's super easy to add more regions. Let's say I started only with 1 or 2 regions and I want to later add third region. It's pretty straightforward and easy. I can go log in into Azure portal, go to my Cosmos DB account, and I can choose whichever region I want. Those all dots are actual Azure regions, and you can just click on it. The moment you click on it, it will automatically get tagged, and the moment you go ahead and save it, it will enable the second region for you, and under the hood it will replicate your database to the other region as well. And the best part out of it is your application doesn't suffer any downtime during this process. You can add or remove your regions on the fly. Enable automatic failover. If you noticed on the top, once you have multiple regions created, it enables the option for manual failover and automatic failover under your replicate data globally blade, the blade that I'm showing here. So once you have more than one region, you have 2 or more regions enabled for a Cosmos DB account, you can manually or automatically failover. It will only get enabled for you if you have more than one region. That's why you can see here write region and read regions. Write region is a region where you can go and write, but you can read. Everything else that you have opted for is a read. You can read from those regions, but you cannot write to those regions. Make sense? But in the region where you can write, you can read as well. So at a time, you can have one or more masters, and the other ones might be just read only. You can failover manually as well, choosing from which region you want to be master or to be primary. It's as simple as choosing the correct region and pressing OK, and it fails over to the secondary region. I'm going to show a quick demo. So I've logged into my Azure portal account. If you want to create an Azure Cosmos DB, there are ways to automate using Azure CLI, Azure PowerShell, or you can use any other automation tools as well. But I've used Azure portal for my demo so that it's more visible. So I can go ahead and create a resource from here, or I can go and create a resource from here. Once I click on that, it gives me an option. It gives me a page and asks me which service I want to create. I can either go to databases and pull up Cosmos DB from here, or I can directly go and search Cosmos here. Once I select Azure Cosmos DB, I can go ahead and create Azure Cosmos DB account. As I was showing in my slide, you have to choose the subscription. I choose my resource group. I give an account name. It validates that it's unique address because it's available publicly, and the FQDN is valid or not. If it's invalid, it will give you a red cross here, but now it says green, which means my FQDN is fine. I can go and choose for whichever API I want to choose it from. I'll stick with the SQL one. I can choose my region, whichever region I want to deploy to. One thing you will notice here is that at the moment I don't see an option for availability zone here. The reason being, availability zone is a feature which is not available in all the Azure regions right now. What happens in Azure availability zones is, in availability zones, within a single region, they have copies of your workloads into different data center buildings, which are running on separate power, networking, water, and whatever supplies are, so that within a region they have multiple data center buildings. If one data center building goes down, the other one is still running. That's the idea behind availability zones. The problem here is it's not supported in all the regions right now, and it's not in West US, which is selected by default. But if I choose a region which has it supported, it gives me an option like East US. The moment I choose a region which supports availability zones, it gives me that option to do it. I can choose Geo Redundancy if I want to deploy or replicate my Cosmos DB account to the regional pair or not. If I want multi-region writes, I can opt here. Or I can choose availability zones. And each one of those is going to cost me a little bit more. And just for demo purpose, I'm just going to leave it. You can directly go and review plus create, but there is another tab called networking, which is useful if you want, which defines how you want to expose your database out of Azure. For example, if you want it to be accessible everywhere, or you want it to be accessible only from your private network, you can configure it here. You can expose it publicly, or you can expose it within your virtual networks in Azure. I'll leave it at all networks right now. And that's it. It goes and submits my deployment, and it creates a Cosmos DB account. It's going to take, I think, a minute or two. I already have another Cosmos DB account created. So once it's created, it looks like this. I can go ahead and add containers in here. If I click on add container, it asks me the database ID, the database name, which is going to hold my container. I can define the throughput I want. We are going to cover it in slide deck later, what throughput is. I can define the ID for my container, and I can also define the partition key as I was showing in the slide deck. You can configure different properties of your Cosmos DB account here. This is the replication thing that I was showing. So as I was saying, if I just go ahead and let's say it's right now running in East US. If I want to go ahead and let's say run it in Europe, I just select that Norway East, and if I click on save, it automatically starts configuring the region for me. It's going to take some time because it replicates the data but it doesn't brings my application down because my primary replica is still accessible. Heard of partitioning? So before I describe how partitioning works in Azure Cosmos DB, we have to understand how it is implemented in Azure infrastructure. Anything in Azure is deployed in something known as Azure regions. As I was saying, there are 58 Azure regions right now. Within each one of those regions, they have data center buildings where they have huge racks, which are known as stamps of servers. It's a collection of huge servers. Within each of those stamps, they divide those machines in something known as fault domains. The idea behind fault domains is that if they divide their racks into multiple divisions, so that if one division goes down because of any failure or any updates, it doesn't brings down the other racks. So it updates basically racks one by one. Within that, have anyone of you used Service Fabric? So Cosmos DB is a service which is built on top of Service Fabric. Service Fabric is an orchestration service from Microsoft, which is quite similar to what Kubernetes does, but it was I think launched almost 7-8 years back, and most of the Azure services are built on top of it. For example, even SQL databases are running on top of Service Fabric. Cosmos DB is another example. It utilizes it for load balancing and service discovery and all that stuff. Within each of the fault domain, it runs something known as cluster, which is nothing but a collection of nodes. It runs on Service Fabric cluster. Within each of those clusters, it has nodes. Nodes are nothing but the machines. In each of those machines, it runs something known as Replica. Replica holds your database engine, your Cosmos DB engine, which also has a JavaScript framework inside it. So any of the tenants or the users who have created a Cosmos DB account, based on the API, they get a collection type. It might be table, collections, graph, or key value, in other words, which is just a logical representation of your containers. Once that gets translated into a container is then actually stored as something known as Replica Sets. That is what you are seeing there. And each of those Replica Sets have 4 different replicas of your collection. The first one is called leader, which is the actual replica which holds your data. And then there are 2 followers, which keep in sync with the leader. And then the forwarder, which points to the other region replicas if it is a multi-region database.
Is this the same way this Service Fabric handles its nodes? Or like same mechanism? Or
In Service Fabric, they also have replica sets, more or less, but the terminology is different. But yeah, it runs on top of Service Fabric, and Service Fabric also handles it on top of replicas and partitions. So important thing to note there is each one of those circles is a resource partition. Whenever we are storing any of the data in Cosmos DB, it goes and sits inside a partition, which is comprised of replica sets. So each of those partition has a property known as partition key, which defines which partition your data goes in. For example, if I have chosen employee name as my partition key, and I am storing my employee record in Cosmos DB collection, then it will create a partition for each of the employee name value that comes there. For example, if it's John, it will create a partition for John. If it's Matt, it will create a partition for Matt. And under the hood, what it does is it takes the partition key, it hashes it, and divides it into the actual physical partitions. So as I was saying, it takes the partition key value. In our case, if it's employee name, for each of the unique value, it hashes it and creates a partition based on that partition key. And these are logical partitions based on hash of the partition key. that doesn't necessarily means that it's going to go and sit into different physical partitions. Multiple logical partitions can share the same physical partition as well. So when I say physical partitions are the actual machines which stores those partitions, and those comes with their own limitations. And each of the partition key that we choose, it's very critical that we choose a partition key which is highly granular, because if we don't choose it in a proper way, for example, if we choose employee name as partition key, there are some first names which are very common. For example, John and Muhammad are the top 2 names across the globe. So if you choose employee name, those partitions are probably going to grow much faster than probably a name like mine, which you will find a very low user set. So the question is, what happens since I said physical partitions have a limitation? I'm going to touch upon those limitations later, but let's say once a physical partition has limitations which are exceeded by our actual resource partitions. What I mean is, let's say we have a logical partition with the partition key as John, and it exceeds the limitations of physical partition. What happens? What happens next? Does it start failing because the physical partition is full, or what happens? What happens is it starts breaking the partitions, physical partitions, into multiple partitions. For example, the moment you see the partition X is reaching its limit, it starts breaking the different partitions out of it. For example, you can see on the left we had many logical partitions up front, but as and when we send our data, upload our data in CosmosDB, the partitions start filling up, and the moment it reaches the physical partition, it breaks it up into 2 different physical partitions, and it breaks the logical partitions among those 2 physical partitions. So that's why when you are designing your data model for your CosmosDB account to be used in your distributed application, you have to select your partition key with the right granularity. The reason being because you can then query based on those partition keys, and if you're gonna, it's super efficient if you query based on those partition keys. That's why they recommend it should be highly granular. There are 3 main motivations behind choosing a partition key wisely. First of them is it should distribute requests appropriately. For example, if I choose something, let's say today's date, if I'm into a business which has records, which has a timestamp, and if I choose that date as my partition key, all my records that are coming in today will have the same date. So it's gonna just keep on filling my partition. Whereas I can, rather than choose a different partition key which is more granular, which is more unique to each of my record, or probably a bunch of records, so that most of those records can go and sit in different partitions, and those can be fetched easily and faster way. Second thing is, we should also plan our partition key in such a way so that it distributes the storage that our CosmosDB account comes with is distributed evenly, and it shouldn't happen that one of our partition is full whereas the other partitions are just lying empty, or they don't occupy much. Thirdly, as I said, based on partition keys, if we can choose partition keys wisely, we can actually write very efficient queries. I will show you later in a demo that querying on a partition key actually brings down the response time, as well as it saves us money as well. Before moving forward, understand what's a hot partition is and what's a cold partition is. When I was saying there might be partitions which has partition key which is overloaded, which has more records, which fills the physical partitions pretty easily, those are known as hot partitions, whereas the ones which are less used are called cold partitions. So it's like we should avoid hot partitions as well as the cold partitions. We should choose partition key in such a way that those partitions are balanced out. Those should not fall under hot or cold. Example scenario, let's take a scenario where if I own a company called Cousteau, which is into a vehicle telemetry, which is a vehicle telemetry company, it has devices or sensors in each of the vehicles it produces, which sends telemetry every second to my CosmosDB account. So what do you think? What would be the ideal partition key that we should choose there? I can give you 4 different options. We can choose a vehicle model, because since I am a vehicle telemetry company, there might be different vehicle models that I'm going to use. So it might be, if it's, let's say, Camry versus Corolla versus RAV4 or whichever it is, I can use vehicle model for that. I can use current timestamp, because it is going to send timestamp every second, so it will always differ. Device ID, since within each of those vehicles I'm going to have my sensors which are going to send me that telemetry information, I can partition my data based on those device IDs. Or I can have something known as composite key, or it is also known as synthetic partition key, which can be formed, as the name suggests, by combining multiple properties if I can't figure out a single property which is unique enough. So which one do you think is the most effective partition key here?
Device ID.
Composite.
Who said device ID? Anyone saying vehicle model? So the problem with vehicle model is most auto manufacturers have a couple of dozen models, so that restricts the range of our partition keys. So what happens is our storage is distributed equally, but the problem is it's not utilized properly, because some models are more successful than the other ones. So the successful models' partitions are uses more storage compared to the models which are less successful. Likewise, the throughput is also impacted because of that. So vehicle model is not a great choice for partition key. Coming to current month, auto manufacturers have transactions occurring throughout the year, and generally they track it based on the month of the year. So what happens is, even though you can see the storage is distributed almost similar way, because every month they have similar sales or it increases slowly, whereas the throughput that you are seeing is for the current month, it's going to be more because the transactions are more real time, whereas for the past months I'm not going to see as many transactions. So it's also not a great choice in this scenario. Coming to device ID, each car would have a unique device ID on the sensor. So this creates a large number of partition key values, because each car will have a unique device ID and would have a significant amount of granularity. So that is taken care of, but the problem is, depending upon how many number of transactions happen per vehicle, it is possible to a specific partition key that it reaches the storage limit per partition. So the folks who said composite key was the right answer. It's because it increases the granularity, of course, because it's a mix of device ID and time, so we get granular data for each device. As well, it has less risk of hitting the storage limitation, as it is related to single month of data, and we are attaching it with the device. We are putting it in a different storage for the past month. It's not only the device data, but we are segregating it on a monthly basis as well. So that takes care of the limitation or storage limitation we get on the partition. So some of the best practices: avoid hot partition keys, and based on what I did some research on, I think we should also avoid cold partitions as well. We should balance it out so that it utilizes both storage and throughput in a balanced manner. Select right granularity, and it is the scope for your transactions and queries. And as I said, if you can choose your partition key wisely, then your queries can be really efficient, as well as they can be fast, and you can save cost as well. So how can you achieve success in identifying your correct partition key? How do you identify if it's right or not? There are few things that you can adopt to come to a right partition key. For example, ballpark your scale needs, understand what type of scaling you need, what is your throughput that you're expecting out of your workloads. So you have to also calculate number of reads per second and the writes per second that's going to happen in your system. For example, IoT devices which sends telemetry every second is too much, whereas some distributed system sends once a minute or once in 5 minutes. So it depends how many reads and writes you're seeing, how many times it reads, how many times it writes. Use Pareto principle. What it says is 80% of your partitions use 20% of your throughput, and 20% of your partitions use 80% of your throughput. So that's why you have to be particular about the partition key that you use here. You can try out POCs. There is a CosmosDB emulator that you can install on your device, on your workstations, that enables you to run your workloads on your system before deploying it to cloud. That way you can calculate the throughput that you are looking for and get an idea of what would be the best partition key for you. And one good part is you should not shy away from creating partition keys. When I said partition keys should be as granular as possible, because there is no limitation on the number of partition keys you can have. Remember I said Azure Cosmos DB is highly elastic. What does that mean is we can have any number of partition keys that we want in our database, and it will keep on creating partitions for each of those partition keys.
So will it be still performant if I have
It will be. Performance depends upon the granularity of your partition key, because if I have let's say if you are querying multiple partitions, it's going to take time, but if you hit your partition using your partition key, it's going to be super efficient because it knows which partition it is going to hit and get the record, As I was saying, the storage limit for each partition is 10 gigs, so take a note of it. What you were asking, Sunil, was it automatically adds partitions, but sometimes it can return 403 errors, so you should know in which cases it can return 403. The first primary reason is when a partition reaches 10 gigs limit and you are still trying to write more data into that partition, it throws 403. That's the primary reason. But there are a few other reasons when it can throw 403, going to be mostly your authorization token is invalid. And if that's not also the case, our stored procedures that we write in JavaScript, they might be failing as well. So in that case also it might return 403s. Request units and pricing. When you create an Azure Cosmos DB, Microsoft bills you for two things. First is the storage and the throughput. When I was saying initially in the starting of the presentation that it provides consistent throughput, that is what I meant, because when we create an Azure Cosmos DB, we define the throughput we want out of our database, and that is what Microsoft charges us for, bills us for. So these are some of the numbers. If we are using, for our storage, it's SSD storage, and for per gig they charge 25 cents per month. For provision throughput for single region writes, they charge under 1 cent per hour per 100 RUs, which is nothing but request units. I'm going to touch in next slide what RU is. Likewise, for multi-region writes, it's double the amount of the single region. And you can provision your throughput two ways. You can either define your throughput at the database level so that it can be shared among all your collections, or you can also provision your throughput at an individual collection level. So as I said, in Cosmos DB, one of the things that we pay for is throughput, and that throughput, the measurement of the throughput is called as request units or request units per second. What it relates to, it's the cost of a request. Generally, if we configure anything in Azure, it's basically the charges for CPU or the memory or anything, any infrastructure or any compute that they are giving it to us. But rather than this is in Cosmos DB, request units is an abstraction on all those things. And what it does is it charges us for the processing power that they are allocating to us for executing each of those requests. Because it is very important to understand what RU is, because it's going to impact your performance of your database. It's also going to impact what you pay for Cosmos DB. You can change RUs programmatically through APIs. Once you configure your database or collection, let's say at 1,000 RUs and you want later to upgrade it to 10,000 or bring it down, you can do it programmatically through API calls. But recently, before I come to that, has anyone worked on Azure SQL databases? Do you use Azure SQL databases? Can you auto-scale your Azure SQL databases? We can auto-scale our web apps. Have you ever tried auto-scaling your SQL databases in Azure? We cannot do it. It doesn't provide that option. But they did introduce something known as Autopilot in CosmosDB, which is super powerful because once you configure your CosmosDB with a set of RUs, you have to continuously monitor how it is behaving and automatically scale up or down the RUs, which is a painful job because you cannot just track how is your database performing. So rather than that, you can choose something known as Autopilot Mode, where what it does is it asks you the max RU that you want for your database, and it automatically configures your database between 10% of that RU to the max RU value. So as I said, each request that we make to our CosmosDB costs us RU, costs us request units, be it a read request or a write request. So if it's a plain read request for a 1 KB document, it costs us 1 request unit, and based on the size of the request unit size increases. Likewise, for a write request for a 1 KB document, it's going to cost us 5 RUs. And depending upon query, I'm going to showcase it in my demo how you can calculate the request units your query is consuming and how you can save some of that. But yeah, it differs for a query based on the complexity and how you are trying to run your query. So the example I took earlier for Cousteau vehicle telemetry company, this is one of the samples from that, the telemetry document, which includes your device information ranging from your car's VIN number everything which gives an information about your vehicle. So let's say Cousteau Logistics has 1,000 vehicles. They send 1 write per second. So I don't know how much each write is going to cost us, but I know there are 1,000 writes per second. So let's say when I test it out, I calculate that each write operation is going to take 10 RUs. So what happens is I have 1,000 writes, each write is going to take 10 RUs. So total I need 10,000 RUs per second. So when I'm configuring my CosmosDB collection, I need to set it to at least 10,000 RUs so that it can process my workload. This is the autopilot preview. It's good for unpredictable workloads. It scales between 10% of the max value we set to the max. And apparently it says that we can set up to 500,000 RUs. It's there in preview is when I checked, or probably it might be out of preview now. And that's the manual one, where we can set it between 400 to 100,000. So how do you measure your RU charge for your query? There are different ways to do it. The first step is to analyze the complexity of your query. Based on the number of predicates that you use in your query, the nature of those predicates, what you are trying to do in your query, the functions that you are using in your query, all those factors combine together to come up with the complexity of the query. Based on that, you can also measure the query cost. When you execute a query, it returns back, CosmosDB returns back a request header called as XMS request charge header, which gives you the request units the query has consumed. So if you execute your query once, you can get how many request units it's costed you. And for the same query, it is always going to charge you same RUs. It never varies for that.
Does the local version that you were talking about, does that provide that when we're doing our initial testing?
It will. I'm not sure if it does. I guess it returns this, but I have tested it out through my C# code when I was running against it. There is a property which I can read it in my C# code. What's the request charge for my query? And I was able to see that. I assume if I would have executed through Postman, it would have returned me that header as well. As I said, it automatically supports the indexing, but we can also have our custom indexing policy based on that indexing, the indices that we are passing in our query. That also defines the RUs that we are going to use. So for example, if I have a record size of 1 KB and if I have 100,000 records, that translates into 100 gigs, which is gonna, if monthly cost was 25 cents, so that I'm gonna pay $25 for my storage charges. Whereas for throughput, let's say if I'm making 100 write requests and 400 read requests, 500 requests in total. For write request, it takes 5 RUs, and for read request, it takes 1 RU because my document size is 1 KB in this example. It's gonna need 900 RUs there. Monthly cost per 100 RUs per second is $6, and I'm gonna use 900 of those. So the total amount I pay is $54 per month. So the total cost for in this scenario for me is gonna be around $79 per month. So when you are calculating your cost for Azure Cosmos DB, do consider your storage cost and the throughput cost measured in RUs when you are configuring it. So I've shown you earlier a database account that I've created. If you'll go in within Azure portal and look for Data Explorer, I don't have any container right now. It is just a blank database account. I can either go ahead and create a container here, but I have a demo here in C# which creates my container as well as it pushes some records, executes a query, and then deletes that record as well. Let me first run it and show it to you. So it created a family database for me. So if I go here, there is my family database which is created. It created a family container within it. It created 2 items in my database. If I go ahead within container and see the items, since I have used Core SQL API, it stores that as JSON documents. So here are my 2 items. If I go ahead and see, I have entered a family, and I have created a family data model in my sample, and it stores it as a JSON, the 2 items that I have stored. One is Anderson and the other one is fake field. So here's a query where I'm passing my predicate, which is where last name is a partition key here. In this example, I have configured last name as the partition key. So when I pass it, it's similar to how we execute our T-SQL queries. It returns my wake field entity. What do you see here is a point read. As I said, if we are going to query based on our partition key, we can save some cost and we can run our queries effectively. I'm going to show you what I mean there. Can you see the code now? So this is where this is the first query which I made on my partition key. So I have created a query for myself. I created a query definition. So when I was saying that we create an account which gives us an endpoint and a primary key through which we can connect to our Azure Cosmos DB. I'm passing it in my endpoint URI and primary key here. Then I create an object of type Cosmos client. Then I create something object of type database, which is also in the same library. Then within that I create a container, and that's what I'm doing in my query here. I went to my container and I iterated through my items using the query definition that I just here, using the SQL query that I created here. It returns me a list of all the items. I loop through that, I query that, and I print it. That is what you saw here, the JSON that I originally inserted. Let me show you how I inserted it as well. I have a family data model that I created with all the properties, which has all the fields that I needed, the properties that I needed for my family object. I have hard-coded it here, but it could come from any source. Once I have my object, I go ahead and do something as read item async. So what I'm doing is I'm first checking if the item already exists or not. If it exists, I just come out of it. If it does not exist, I call something known as create item async on my container. I pass the family object I created there. I define what is my partition key gonna be. In this case, I have defined it as last name. So this was the first example where I fetched it based on query. The other way, since I only have 2 records and I know what's my partition key is and what's my ID is for my record, I can do something known as point read. I'll just show you how beneficial it is, but this is how I do it. I read the item as sync and I pass the ID for my document and the partition key. That's it. Within that partition, it goes and finds the item with this ID and it returns it back. I'm gonna show you how it translates into RU. This is the request charge property. Whenever an item is written, it comes with a request charge value in that. How much RUs it consumed while returning back or executing that query. Let me uncomment it and show you how much it took for each of those. So I'm gonna run the same demo again, but this time I'll show you how much RUs each of those operations took. So it created my database again, because in the initial demo, after all the operations were done, I have deleted my database and collection. So when I inserted my first record, it took 12.57 RUs. When I inserted my second record, it took 14.48 RUs. When I ran my query through SQL query, it took 2.9 RUs. Whereas when I run it based on point read, when I exactly knew the item I needed, when I passed the ID and partition key, it just took 1 RU. Just imagine I can run 3 point reads at the same expense of my previous query. Through that, the result is returned faster and I save down my cost. I can run 3 queries at the cost of 1. When I'm updating it, it costed me 11.43. When I deleted one of my record, it costed me 14.48. So you will notice that it took exactly the same number of RUs it took for creating that record for me that it took for deleting. So yeah, that's the property you can use to analyze how much your queries are gonna charge you RUs. So keep a hold of it and come up with an estimation of how much RUs you are gonna consume, because it will impact your throughput as well as it will also impact your costing. All right, anyone knows what is CAP theorem? So what CAP theorem says, any system, any distributed system which is distributed across replicas or partitions, it can only provide you consistency or it can only provide you availability. Consistency is if I have multiple replicas of my database, it's gonna return me consistent value irrespective of whenever I access. It always gives me the last committed write. It never returns me an uncommitted write value from any of those replicas. It has to be consistent across all the replicas whichever I connect to. Availability is every request receives a non-error response. If I hit it, it goes to the database, it hits it, and it comes back. It is available always in case of any disaster or not, because it's partition. And the CAP theorem says either we can get availability or we can get consistency, because if its availability is our priority, then both the replicas might not be consistent. And if we want both replicas to be consistent, we will never get availability because one of them will be down. Then there was a theorem called PSELC, which extended CAP theorem, which says apart from CAP theorem, which says in case of network partitioning, a distributed system can only provide availability or consistency. If it's not partitioned, then you have to choose either between latency or consistency. So how this theorem translates into is, if you have a system which is distributed, you have to choose between availability and consistency. If it is not distributed, if it's not partitioned, then you have to choose between latency and consistency. People who have used NoSQL databases or any database, how many consistency models you are aware of? Out of strong consistency and eventual consistency. That's pretty much supported by most of the NoSQL databases at least. So Azure Cosmos DB is the only database which provides 5 well-defined consistency models. When I spoke about strong consistency and eventual consistency, those are the two different extremes of how we can achieve consistency. What strong consistency says is it provides, it ensures that it never returns uncommitted write. It ensures that if it's a partition or a distributed system, if you send a write, it gets returned to all the replicas, otherwise it never gets returned to it. It's just discarded. Whereas eventual is, no matter what, if one system goes down, at a later stage it will eventually become consistent among themselves. So strong consistency ensures all your replicas are in consistent state. Eventual consistency says it will in future become consistent eventually. Whereas there are 3 more consistency models which are available in Cosmos DB, which fall in between strong and eventual, which we can use in our Cosmos DB or distributed systems. The second most important is bounded staleness. In most simplest term, what it does is it defines a staleness window, after which it starts behaving as a strong consistency model. How that sliding window is defined, it is defined based on 2 criteria. One is, at most it can have k prefixes out of order, or it could be at behind certain time interval of the consistency. Session is where it maintains a session token and it maintains consistency for a particular session. Consistent prefix is results will always be in order. They will, irrespective of if they are not consistent, but they are somewhere in order and they will sometime get eventually consistent. I already covered strong consistency, which I hope everyone understands. It offers linearizability guarantee, where it is guaranteed to return the most recent committed write. It never returns uncommitted writes. Eventual consistency, it guarantees that eventually it is going to be consistent. What is bounded staleness? I said it maintains a sliding window or staleness window. It provides a stronger consistency guarantee than session, consistent prefix, and the eventual consistency. The difference between strong consistency and bounded staleness consistency is, you can think of strong consistency is also bounded staleness consistency, with the condition that the time window is 0. So it's always consistent. Whereas for bounded staleness consistency, it has a window longer than 0. In Azure Cosmos DB, you can log into Azure portal, go to your Azure Cosmos DB, and you can define if you want to choose bounded staleness consistency. If you opt for that, you can provide the maximum duration of lag that is acceptable in your database, and as well as the time. So when I say maximum lag, it's in operations, that how many operations it can lag behind consistency, and how much. Then you can also define how much time it can lag behind. Session consistency, as I said, it remains consistent for an individual session, even though it's not strong consistent, and eventually it gets consistent once all the systems are up. In your code, you can provide something known as session token, which you can link with your request so that it is always consistent for your session. Consistency prefix, it guarantees that in absence of any further writes, the replicas within the group eventually becomes consistent. So what happens under this is, if we have opted for consistent prefix, and let's say the writes were performed in the order A, then B, and then C, the user is going to get either A or B or A, B, C. He's never going to get something which is out of the order, like he cannot get return A and then C. It is always going to return back it is always going to return back in order. It might lag behind by certain prefix, but it will still be in the order that it's going to be consistent later. We can set consistency level not only at the collection level or the database level, we can also define consistency at each of the request level when we are placing that request. by setting the consistency level within request options parameter within our query, which is super helpful. So when we have our CosmosDB conflicts happening between multiple replicas, there are few ways we can resolve it. The first option is that we can set something known as last writer win, which means is the last write, the last committed write wins, whereas the other one's not. So that it replicates the last write return value everywhere in all the replicas. The second is if we don't want to use that, we can also have our own custom stored procedure to take the to make the records consistent among themselves or resolve the conflicts. If we cannot do that as well, then there is something known as a conflict feed. So that what happens, the records which remain in conflict, they go and they are logged into a conflict feed, and we can go ahead manually and check it out what were the conflicts and resolve them manually. So as I said, if we are going to use last writer wins, then we can specify the resolution path, that on which ID or the which property we want it to be resolved for. If we are going to use a custom one, we can define the stored procedure name we want to execute as part of the conflict resolution. Like in this case, I am specifying that my resolution procedure is a stored procedure with name resolver, which under the hood is mapped to a resolver.javascript.js file. As I said, within the CosmosDB database engine, there is a JavaScript framework running, which enables us to run all these stored procedures and user-defined functions. And if we want to feed it into conflict feed, we are deleting the conflict. We are reading the conflict first using container.conflicts.read conflict content. We are merging it using our own logic. We are replacing items or merging items, whatever we want to resolve the conflict, and then we go ahead and delete the conflict from the conflict feed. Just on the lines of conflict feed, there is something known as change feed. Out of event streams, it's not exactly the same concept, but if you know what event stream is, it will help you in understanding. It's a similar idea. What change feed does is it has, whenever we make any changes in our CosmosDB, it logs all those operations in something known as change feed. It tracks all the operations that has happened in our CosmosDB containers, and which we can actually then take it forward for multiple use cases. We can use it for event computing and notifications. We can use it for stream analytics. We can also use for extending it to our enterprise data movement. So it's a pretty cool feature. It tracks all the changes happening in your CosmosDB, and you can trigger events based on that. If you are using CosmosDB in your application, how do you troubleshoot if it's giving you some errors? One thing is go to your CosmosDB account and set up diagnostic settings. If time permits, I will show you how we can do that, and you can take all the telemetry, all the metrics data out into a storage account or an event hub or into a log analytics workspace, so that you can further troubleshoot what's happening in your database. And if you have not used Azure Monitor or Log Analytics, I recommend you go and do it, because once you start dumping your metrics data from any of your Azure resources, including CosmosDB, then there is a query language called Cousteau query language. You can start querying your logs within Azure Monitor. This is someone was asking if we can see the hot partitions. So this is how we can see the RUs that my CosmosDB collection is consuming. It's within the Azure CosmosDB blade itself that I was showing earlier in the portal. Under metrics, you can see the RUs that it's consuming. Likewise, we can also see the data and the indexes that are built up on each of my partition. I think I messed up with my slides, but one of these shows the RUs, and the other one shows the hot partitions as well. I think I may mess up the title with this slide. So title says hot partitions, but the slide says, the screenshot shows RUs. But likewise, you can also see hot partitions. It shows you under the metrics. When you are developing using SDK, CosmosDB SDK in your project, there are some best practices that you should follow, which first and foremost, whenever you are creating a Cosmos client, ensure that you use a singleton object. Use direct mode, which is a feature of SDK version 3. Set application region. What happens in CosmosDB is when we make API calls for our CosmosDB to read and write data, they are known as, it's smart enough that it identifies which region is the nearest region for the request. Then it automatically goes and performs the operation in the nearest region. For example, if I'm in central US region and I'm making a request from central US region, it automatically identifies that my nearest region is central US, and it goes and performs the operation on that region. If that I have selected a region in my CosmosDB. Otherwise, it identifies which is the nearest and it performs operation on that. Tune max degree of parallelism. Use point reads. I showed you. It's just no matter how you perform point read, it always takes one RU, whereas your other queries can vary from any number of RUs depending upon the complexity. So use point reads wherever you can, and use parallelize it wherever you can, so that you can, especially it matters when you have huge number of records to be written. It makes sense to make them parallel and execute them in parallel. Yeah, so if you are moving into production, add a second region if you are looking for 5 nines SLA. If you want to stay in single region, it comes with 4 9 SLA. The difference is 10 times. 5 nines means 5 minutes downtime, and 4 nines means 52 minutes. It depends upon the case-to-case basis. For some cases, 4 nines are okay. And as I said, I've shown earlier how you can add a second region. Some of the use cases where CosmosDB is really useful is if we want to distribute data and make it available globally. We can have an arrangement where we have multiple web apps which are running at different regions. They can write into this single region, CosmosDB, or multiple regions. We can build real-time customer experience sites or services which can feed data into CosmosDB. We can use it for gaming, IoT, and e-commerce use cases. I've taken all these reference architectures from Microsoft's reference architecture, so if you want, I can pass on the information. You can go and check it out, how you can implement CosmosDB in each of these. And as I said, our example was also around telemetry. We can use it for IoT telemetry use cases. We can use it for serverless architectures. Azure functions, if you have used, we can utilize Azure functions with CosmosDBs and come up with serverless architectures. And it also supports Spark now on top of CosmosDB, so we can run Spark over our operational data using Spark API. Thank you.